Rapid advancements in artificial intelligence technology are paving the way for more sophisticated imaging solutions. Innovations in machine learning and computer vision will further improve medical imaging practice. The future of medical imaging holds exciting possibilities with the continued integration of deep learning technologies. Understanding these advancements can lead to improved diagnostics and patient care. Further research in AI for medical imaging holds the potential for breakthroughs that could redefine diagnostic capabilities. Various mathematical models, such as random transform and convolution models, are employed in image reconstruction. These models help in accurately interpreting the data collected from the imaging modalities. All medical images are acquired when there is an interaction of energy with tissue, which is recorded. The interaction of the tissue with the energy is recorded in analog and needs to be converted to a digital format to be utilized with computers. Digital imaging relies on principles such as sampling, quantization, and representation of images in pixel format. These principles serve as the basis for reconstructing images from raw data. Here we see an analog to digital converter, taking the original signal and changing it into an image. Sampling, taking samples or measuring continuous time signal at discrete times, is called sampling. Quantization is the assigning of a value to each discrete time signal. Coding is the assignment of a binary digit sequence to each discrete output from the digitizer or quantizer. The signal strength of the energy differential or the interface interaction is recorded as an electrical signal. The strength of that signal is proportional to the strength of the interaction of the energy. This forms the latent electronic image. Sampling measures the intensity of each pixel or measures the attenuation profile of the anatomy at a given time interval. When we sample the interaction of the energy and the tissue, we are recording the raw data at specific points upon the body. The pixel intensity is a reflection of the raw data that we've recorded. This sampled data is stored in the computer, which is a storage space made up of lines of data that we can draw upon to create the images through algorithms. The Fourier transform makes digitization possible. The signal to be digitized is sampled several times and then averaged. This mean, or the average, is used as the digit number which represents its strength. So a digital image is not an exact snapshot of reality. It is only a discrete approximation of the reality at that specific time. When we use a digital process, or digitizing the different signals, we have a process which is different than the photographic process. Here we can see the difference created by the amount of signal collected. Let's look at the same image with different amounts of signal. Notice with too little signal we get quantum model or a noisy image. Whereas if we have too great a signal, we start to lose detail. Let's take the information we have and utilize that in an analysis of medical imaging. In this analysis, we will compare the results of AI-enhanced imaging with classical techniques, illustrating the clear advantages of employing AI in medical imaging practices. Challenges such as image noise, motion artifacts, and limited data can significantly impact image quality. Addressing these issues is vital to enhancing the diagnostic capabilities of medical imaging. There are various types of medical images, including X-rays, CT scans, MRI scans, and ultrasound. Each type has a unique characteristic and application, contributing to comprehensive understanding of a patient's condition. We are moving on in medical imaging, focusing on how deep neural networks enhance image resolution compared to traditional measurement techniques. We will discuss various methodologies, comparative analysis, and future implications in the field. In this analysis, we'll compare the results of AI-enhanced imaging with classical techniques, illustrating the clear advantages of employing AI in medical imaging practices. We'll explore the transformative role of deep neural networks in the field of medical image reconstruction. We will cover the significance of medical imaging, examine various neural network architectures, and discuss their application in enhancing imaging techniques. Once the medical imaging modality has recorded the data, we will select data to create an image. All the data can be selected, or segments of the data can be selected. We will take this data and utilize computer algorithms to enhance it to create the image of the area of interest. Despite advancements, challenges like noise, artifacts, and limited resolution persist in image reconstruction. Addressing these challenges is crucial for improving image quality and diagnostic accuracy. The basics, sampling, quantization, and pixel representation are the principles that serve as the basis for reconstructing images from raw data. Algorithms play a pivotal role in processing imaging data and reconstructing images. Efficient computations ensure that complex data can be translated into usable visual formats. FBP, or filtered back projection, involves filtering projection data before back projecting it to generate an image. This technique enhances the clarity of the reconstructed image and is foundational in CT imaging. Here we see in a cross-section of a thorax. B, C, D, E, and F show us how we utilized the information and created that image through filtered back projection. Filtered back projection is primarily used in computed tomography, but can also be adapted for other modalities. Its versatility makes it a staple in various medical imaging applications. Another powerful method of reconstructing images is the technique of iterative reconstruction. It's primarily used in medical imaging using gamma rays or nuclear medicine, but is also being utilized today to enhance the images of MR and CT scans. Iterative reconstruction techniques offer an alternative approach to traditional methods, focusing on refining images through repeated processing. The iterative method involves estimating and updating the image progressively based on the available data. This approach allows for better handling of noise and artifacts compared to traditional techniques. Iterative techniques often provide superior image quality and are less affected by noise. These advantages make them particularly beneficial in complex image scenarios. Fourier transform techniques are fundamental in image reconstruction, allowing for the transformation of spatial data into frequency domain representations. The Fourier transform breaks down images into their fundamental frequency components, enabling deeper analysis and manipulation. Fourier transform techniques are implemented in various reconstruction algorithms, facilitating the manipulation and enhancement of medical imaging. A comparative analysis of techniques, including filtered back projection and iterative methods, reveal their strengths and weaknesses. This understanding is vital for advancing medical imaging practices. Identifying limitations in current reconstruction methods is crucial for driving innovation in the field. Areas such as noise reduction and computational efficiency require ongoing research and development. As technology evolves, emerging trends like artificial intelligence and machine learning are expected to play a significant role in enhancing image reconstruction techniques and paving the way for more accurate and efficient imaging. Deep learning techniques can significantly speed up the image reconstruction process, allowing for faster diagnosis and treatment planning. This efficiency is particularly valuable in time-sensitive medical situations. Future advancements may lead to more sophisticated models that can handle increasingly complex imaging tasks, expanding our ability to manipulate images, making imaging faster and more accurate. As deep neural networks become more prevalent in medical imaging, ethical considerations such as data privacy, consent, and the implications of AI in clinical decision-making must be addressed. Integrating deep learning with other medical technologies such as robotic surgery and telemedicine could lead to transformative improvements in patient care and outcomes.